So welcome to our next tutorial on architectures of AI systems. Today we are going to cover three topics. Firstly, basics of AutoML with AutoGluon. Second, data drift and model drift detection and model retraining. So let's start. As I already mentioned, there is a very interesting set of different solutions which enable you to automate machine learning training. Among of them, you will find solutions like PyCaret, AutoKeras, or AutoGluon, which is my choice for today. This is created by a group of people from Amazon, but obviously it's open, so it's a community supported solution. If you look at this website, you can see it now, AutoGluon. You have installation recommendations. As you can see, it supports at the moment Python 3.8, 9, 10, or 11 on different platforms, and we are going to go through this, use these instructions to install it in our system. But also you'll find here very interesting tutorials like tabular quick start, which I strongly recommend you to later on give it a try, and even multimodal quick start or time series quick start. So these are quick starts and more advanced tutorials. So these are very, very useful and will show you hopefully the power of this solution in production. So let's start. In order to run our model using AutoML or train the model using AutoML solution like AutoGluon, we need to install it in our environment. I already did this, but if you'd like to go through the precise installation instructions, you need to be a bit patient because it requires many different libraries that are interconnected. So probably the best choice for you would be to use the recommended by AutoGluon solution using the Mamba package manager, but it takes few minutes to get the package from the Conda Forge channel. So I already did this, just a technical thing, and I have at the moment it installed in my Kedro virtual environment, which I also use for machine learning pipelines. And we're going to start with the first script where we are going to train the simple machine learning model on our training data set. So once again, let's have a look. We have here the data folder with training subfolder, and in this subfolder I have customers labeled dataset. Once again, this is our toy example where we train the model to predict whether a given customer will be high revenue or low revenue. And we have different features of the customers, of the internet shop or internet store which sells globally t-shirts. And we have data like customer ID, gender, campaign, IP address, country, so country it comes from, pages visited during, on average when they visit, age at the first order, browser used, operating system, and variable we'd like to predict. So you know this example. Previously we spent a lot of time on data prep, choosing and training and evaluating model. Now using AutoGluon, as you can see, it's just a single line of code. After the imports, I just simply import the train data and call this single line where I fit a model, optimizing it on ROC, IOC receiver operating curve, area under the curve, yes, on the training data, pointing to high revenue column in this data frame as a target variable. So as you can see, the training is done literally in a single line. The training and the feature engineering, data prep, everything is done literally in a single line. So this is the magic of AutoML systems. So now let's give it a try. Let's try to train it and see what happens. As you can see, it's starting fitting 13 different models. It chooses different models, yes, it validates those models or receive an operating curve. As you can see, there are some also neural networks being trained, XGBoost. Obviously, they gave us different results. Yeah, and we have it trained. As you can see, the best model is weighted ensemble L2. So this is ensembled model where we combine results of different models with different weights. Yes, with this ensemble weights, as you can see, we have CANBoost here, Neural Net Torch, XGBoost, LightGBM, etc. So we have different models combined. Since in my future use cases I'm gonna to retrain it very often, I decided to later on ask in our retraining pipeline to use only a single model out of them, just to repeat, not repeat all this training process with training different models. It's possible with this snippet of code. As you can see, the only thing I have changed is that I added some hyperparameters here to the predictor pointing to XGBoost. XGBoost is a very powerful algorithm which is very close to this weighted ensemble at 2. So I'm gonna use this single model in our future releases. So now let's give it a try how it works. Yeah, it's there. So as you can see, AutoGluon has created, and we can see it here, an extra folder at the very top where it stores the model. Yep. And later on, we can use this model as a predictor, just simply calling this from this path. Yep. So as you can see, this is a very specific path here, but I wrote a simple helper function which for the future use simply, as you can see, this is the timestamp with the hour, minute, etc. So later on I created a simple helper function which tracks the folders with these models. As you can see, this is the folder with the model. We have with the metadata, with the pickled model. Yes, here it is with the timestamp. So whenever I call later on such a model, for example, for the evaluation purpose, I track the content, I track those names, I extract the date, and take the newest one as the one used to predict, to evaluate, for example, to be evaluated. But it's just a technical thing. At the end of the day, we have trained the model, we have it stored somewhere, we can call it for prediction. So this is the first step. Our next step is to simulate weekly data which are distorted. Yes, distorted. So we're going to use for that this file 2.distortpy, where we import at the very beginning original data from our original customer's labeled comma separated value. So this is our original data set with data on a bit more than 10,000 customers. And since this is the simulation, we are going to simulate the feature drift. Yes, we're going to create a set of distorted data sets. At the moment this list is empty. And then for week in range of 1 plus weeks, at the moment the default is 21. So I just simply simulate something like a half a year of weekly data. And as you can see, you can read it later on more carefully. It's quite self-explanatory, but I distort the pages visited number. I distort age first order with some random number distribution, yes. I also make some more aggressive adjustments to categorical features like sample size. This is sample size, but browser location, etc., operating system. And at the end of the day, I get a set of weekly data stored in this folder. It's at the moment empty, but let's have a look. One important thing. So whenever I distort data within a given record, I distort different features. I keep the target variable high revenue intact. That means that in that sense, this is distorted. So the same result will be provided by different values of the feature. So this is the idea of the distortion. Obviously, reality will distort it on its own way, but I need to cope with some simulation here. So let's do this. Let's call this 2-point distort. And now, as you can see, if we reload the folder here, I have 21 data sets with different data. Moreover, this distortion is based on the previous week, so this distorts that one, etc. So it should be progressing. So this distortion should be progressing in a way, in some sense. Very good. So we have the distorted data set, and now we have the fed script, which is just used to evaluate without any detection our model, our original model, that one we trained using 1.trainPy on the subsequent weeks. And for that, we are using metrics from scikit-learn, ROC, AUC score, receiver operating curve, area under the curve score, and accuracy score. This is the helper function I already mentioned before. So I take as a model directory this AutoGluon models directory. I sort them. I extract the latest model path and call the predictor from this latest model path. Yes, and then I create a new metric file. It's gonna land here in the drift detection. Yes, system. And I will store data on, so maybe I'll need to remove it. Yep, just to clean it up. I will store data with the accuracy of all those previously stored models. So as you can see, I go through all the weeks. Yes, I prepare data for evaluation, I compute and return those two values, print them also on screen. So let's run the script. It just we are not going to use it in production later on, but just to check whether we have a kind of the drift in our accuracy. Let's have a look at the results. As you can see, there is almost no drift in the accuracy, yes, but there is a significant visible drift in receiver operating curve area under the curve. That's probably because we have trained this model AutoGluon focusing on ROC, AOC as a key measure, and then when we distort the data set, this measure decreases, but obviously it needs some extra diagnosis. So, wow, what do we have here? We just now have a simple diagnostic tool which will help us to print out on screen a week by week those two very important measures for us, but moreover, it also stores them here in this folder. As you can see, I have a week, receiver operating curve, under the curve, and accuracy, two different measures, and I can keep those values either on my drive as a text file and append week by week those numbers, or as we saw already, or we see in a few tutorials from now, professional systems like MLflow experiments, MLflow tracking, apologies, or weights and bias. So that's that. And now it's time for something a bit more serious. We have here the next file for .detect drift pi. And what do we have here? Let's have a look. We have the following function: evaluate and save metrics. So it once again, as the previous script, computes and saves evaluation metrics for each week. Yeah. So I call it with the week number as a parameter. Predictor is my current model, and metrics 5 is which is the path to the system, to the file. Yeah. Where I'm gonna store this result. So it's quite easy. You saw this a few minutes ago, but now I have an extra function which is key in our computations now: detect drift and append signal. And I have 4 different tests implemented here: hard test, parameter test, IQR test, and absolute test. I want you to refer to the details of those tests in my lecture, but as you can see, I have some controls here which enable me to turn on or turn off those tests during the drift detection, because some of them may be oversensitive. And let's have a look. Hard test. Hard test is triggered. It detects the drift in case a current week value of the parameter, whether it's accuracy or receiver operating curve, is lower than mean of all the previous ones. So as you can see, for that computation we need to skip the first week, yes, because for the first week we do not have history, yes, so it takes into account some history. So whenever for a given week a value of the score is lower than the mean from all previous ones, we'll signal the drift. It's very, very sensitive, yeah, so it's sometimes oversensitive. Parametric test is a kind of the outlier detection, yes. As you can see, we identify outlier as a value which is beyond some normal measure. As you can see, it's defined by mean minus 2 times standard deviations of all other values. So that's why we also need some history here. Yes. And for non-parametric IQR test, we have similar approach, but with quantiles, with 1.5 times IQR accuracy. And for absolute test, which is quite reasonable, very popular, yes, this is the simplest one. We define some acceptable by business a measure of a given score, like for receiver operating curve, area under the curve, we can set it up as a fixed value of 0.81, or for accuracy 0.9, and say, okay, trigger the alert in case the value is lower than this value, which is hard coded here. Yeah. So these are those metrics, and then that's quite straightforward. Python code. The key point is here that we scan all the weeks, we trigger, we compute the scores, we save them for the future purpose. Since for the week 4 we need some stats from the previous 3 weeks in order to compute, for example, the mean or standard deviation, yes, and print out the results. So let's give it a try. And yes, we have some results. So let's have a look at them. For week 1, no drift, natural. For week 2, no drift. For week 3, wow, We have a drift detected for week 3 due to hard test inaccuracy, parametric test inaccuracy. Next weeks are clean, but then I have a drift detected for week 6 due to absolute test in error CFC. Yes, so as you can see, this is 07991 compared to 8105. So that works. So now let's give it another try. I will turn off the hard test and parametric text because probably they are too oversensitive. So yeah, as you can see, hard test false here, parametric test false. Okay, let's save it and call it once again. So yeah, there are no alerts. Yes, there are some extra alerts, as you can see, for week 2 at the moment due to IQR test in ROCIC and IQR test in accuracy. So we can also turn them off because they are also very sensitive. I need to, at the moment, remove this. If it is there, let me check the historical model version just not to append the data. So now, once again, let's give it a try. And now, as you can see, I have only absolute test and the drift is detected only for week 6. Okay, so it's up to us how to cope with those tests. We have a simple script which detects the drift. And this is a very good basis for the next trick we are going to use in the full ML ops pipeline, machine learning operations. So, as I already mentioned during my lectures, the goal is to automate retraining. And for that, I have created 2 new extra files. Firstly, 5 detect, drift, and retrain, which is just a very slightly modified version of this 4 detect, drift file. The slight modification is here with the single line at the very bottom. Where we call, look, if combined data drift detected is true, yes, we call here a sub-process run, yeah, Python retrain model py. So what does it mean? Python has a library called sub-process. It enables Python script to run an external shell command from within the run. So this command we are going to run here will be Python space retrain model with some parameter which is the week number. Yes, we can call the Python with the parameter, and this parameter later on will be taken as the input as a script. So whenever the drift is detected, we are going to call an extra process, external process, retrain. And this retrain function is here. So it prints that the retraining process has initiated. Yes. And then it calls our well-known AutoML training functionality, yes, with the week as a parameter with XGBoost, yes, and saves in a natural way this file into our AutoGluon models folder. It's gonna create many different models. So now let's have it run. So let me check only the one thing. What are the parameters of, yeah, we have use hard test false, param test false, IQR test false, so I keep only absolute test true, just not to have the model retrained all the time. Yeah, obviously in the production it's up to you what type of the train you are going test you are going to use. And now let's call it. Okay, as you can see, it works. It checks for the drift. In case the drift is detected, it calls the retraining process and saves an appropriate model in AutoGluon directory. So let's wait until it completes the job. Yeah. And the final check, let's have a look at this model evaluation metrics. In my script, I made some extra tweaks. And in order to bring you a bit closer to real life production scenarios, I've shown you the typical log of such a model. This is the very simple from technical point of view solution, but it really works in practice. Obviously, you can use a bit more advanced solutions like model repositories, model tracking, experiment tracking, whatever. But this is the very, very easy solution you can use here and now without any unnecessary technology overload. Look what I have here. I have a week number. Yes, this is the first number. Next, I have the value of the ROC, IOC, and accuracy, two most important metrics for me as a second two values, the second and the third one. Then there is the information whether the drift was detected. It is false and there is no drift. And finally, the version of the model I used for this week. And then, in case the drift is detected, as you can see, yes, so it is true, I have the reason why it's detected. If there are multiple reasons, because there may be multiple values affected, yes, the drift may be signaled because of multiple different tests. I will keep them in record. In this record, obviously, I have turned off some other tests. I kept only the absolute test here just for sake of simplicity. But here there is also another model which is the result of the retraining. So I have everything in one place. So that completes this simple tutorial. I shown you three things here. Firstly, that you can use very easily AutoML solutions like AutoGluon for your pipelines for the feature engineering, data preparation, and model training. Next, we created a very simple script to simulate distortion of the data. Obviously, in real life, you won't need this. You just simply use your live data, and the script which evaluates the data. So I get some predictions at the very beginning of the week, for example, and then I compare those predictions with the real values at the end of the week. I can compute receiver operating curve for accuracy, or whatever measure you want for regression. That may be RMSE, it's up to you. Next, we have created a script which detects the drift using four different types of measures, and finally it triggers the retraining process using the subprocess module, which calls the retraining script. So that's that. It's very, very easy implementation on the whole pipeline. I hope you'll find it useful, and good luck in your future experiments. Thank you.